part 2 of the notes, we'll talk about capacitors and series and parallel circuits. This is on page 5 through 8 through your notes. A capacitor, this is all review. This is what we talked about. You had a test over it. I'm throwing it back in there just so you know it. A capacitor is a device that can store electrical charge. It consists of two conducting plates that have billions and trillions and trillions of charges on it. You will have a positive and a negative charge. They're going to be close to each other. And it's going to have a uniform electric field across to it. And instead of using V equals IR for capacitors, we're not going to use that. We're going to use QVC, home of the shopping channel. Ha, my attempt at a terrible joke. Q is going to be the charge on one of the plates. The plates have to have the same magnitude of charge, just one of them's positive and one of them's negative. V is going to be the potential difference. That's going to be the potential difference between the plates. And finally, C is the capacitance. It describes how that capacitor is made. And so that capacitance, that capital C, is the rating. The SI units are going to be the farads. Most of those capacitors go from the pico to the microfarad units. And it depends on how it's made. Again, you had that formula last time. Throw it back in there just so you can see it. Let's work this problem just to quickly remind you of that formula. Calculate the capacitance of a capacitor whose plates are 20 by 20 by 2 centimeters and are separated by a 1 millimeter air gap. Our area here cannot be in centimeters, have to be in meters. So 0.2 times 0.02 gives us a value of an area of 0.004 meters squared. That constant, 8.85 times 10 to the minus 12 times my area, 0.004, divided by my distance between them. Again, that needs to be in meters. And so I'm going to stick 8 times 10 to the minus 3 in there. So as I'm plugging this into my calculator, I will get a value that is going to describe that capacitance of that now I'm tongue-tied. I got 3.5 times 10 to the minus 11. Again, that SI unit is farads. Part B, what's the charge on each plate if it's connected to a 12-volt battery? Now that I have the value, I can use Q equals VC. I can calculate that charge by multiplying that value of that capacitance that I just got by my 12 volts. And when I do so, I get Q to be 4.2 times 10 to the minus 10 coulombs. The last little bit, what's the electric field of this? Hopefully you remember this equation from last unit. V equals ED. There's a uniform electric field being produced there. It's connected to a 12-volt battery. The distance between the plates is 0.001. And so when I do that math, I get an electric field to be 12,000 newtons per coulomb. Again, hopefully this is a review from what you saw last time. We also have potential energy stored in the capacitor. That's 1/2 QV. And then if you know that Q equals VC, I can substitute that in for Q and get the second formula for that potential energy of a capacitor. A capacitor are seen lots and lots in real life. The easiest way to remember capacitor, remember those old flashes, or even the flashes on the disposable camera. You push a button and you hear this noise. That is the capacitor charging. Once that little light comes on, it says, ooh, I have all of my energy. It's stored. I can release the button, and that energy will be converted into, in the case of the flash, light. On this problem, a computer flash unit stores 150 microfarads at 20 volts. How much energy can be stored? I'm given C. That's going to be 150 times 10 to the minus 6th. The potential, 200 volts. That will allow me to use the potential energy equal to 1/2 CV squared. So 1/2 times 150 times 10 to the minus 6 times this 200 squared. And so when I do the math, I get a value equal to 3 joules. Okay. We are fixing to draw lots and lots and lots of diagrams, so we need to have the correct proper notation. A potential different source is going to be a long line with a short line as well. You need to know that the long line is the positive terminal of the battery. The short line is the negative terminal of the battery. A capacitor is going to be two parallel plates, just like a capacitor is. A resistor, the little squiggly line. A wire, plain old wire. Sometimes you'll see a light bulb written like this. Sometimes this is referred to as a light bulb. An A with a circle around it. You need to know that that's an ammeter. Guess what an ammeter measures? An ammeter is going to measure current. Write this down now because you're going to need it later. It must be wired in series. Make sure you know an ammeter has to be wired in series. A V with a circle around it is known as the voltmeter. Guess what the voltmeter is going to measure? Volts. Very good. And it has to be wired in parallel. The next topic of conversation is our series and parallel circuits. And let's see what you remember about those. In this series circuit, as this picture down below right here, there is only one path for the electrons to flow. It's going to leave this positive terminal. It must go through this light bulb. It must go through this light bulb. It must go through this light bulb and back around. Only one path. These are the three things you have to remember about that. Actually, four now. I is going to stay the same. The I going through the first light bulbs, the I going through the second, through the third, and so forth. The voltage gained by the battery has to equal the voltage dropped by the resistors. So if this is an 18-volt battery and there are three identical resistors, what's going to happen? How much is each one going to get? Hopefully you can see that each one is going to get 6 volts. So if I was following along the path here, these electrons have 18 joules per coulomb of energy. Now, how much of it gets used up in this first light bulb? Hopefully you can see that 6 of it gets used up. And so at this point right here, how much potential do I have at this point A? Hopefully you can see that I have 12 volts left. Then I go through this next resistor. How much is going to get used up? Another 6. So I'm here at point B. What do I have left? I have 6 left. As it goes through here, it has 0. So then at C, I'm down to 0 volts. Goes through the battery, get charges back up and around. So what this shows me is the voltage provided by the battery has to equal the voltages through each resistor. If we want to replace the resistor with one total one, the total resistance, I would add up all the resistors. And capacitance, this is something that you have not seen before, but we can wire capacitors in series and parallel. In this case, it's going to be wired, they will be additive. They're the reciprocal functions. So 1 over C total is 1 over C1 plus C2, vice versa. What is the problems with a series circuit? I don't know if you remember the story, but my first year at A&M, actually my second year at A&M, we got an apartment. Loved the apartment. It was huge. Compared to the other departments that I saw, this one had great big living room, 2-bedroom, blah, 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 blah. We finally get moved in, and we go into the living room, and we find out something very interesting. This apartment was wired completely and totally in series in the living room. So what does that mean? Every single plug in the living room is either on or off. So you either had all the lights on and the TV on at the same time, or you had to unscrew the light bulbs. It was a pain, but it was cheap. The next type of circuit that you're going to see is a parallel circuit. As you can see, the parallel circuit has many paths. There's some vocabulary words that you need to know. These little dots that I'm drawing right here are junction points. These junction points is where the current splits. Some of the current's going to go to the right, so it's going to continue along this path. I reach this next junction point, some of it's going to go through that light bulb, other of it will continue along the path. So the current chooses the path that it wants to go through. The voltage stays constant, so each path is going to get the same amount of voltage going through it. The current, however, will be additive. So what this means is what is coming into the junction point has to equal what leaves the junction point. And so if I have this path right here, and I start off with 6 amps of current, this path gets 2 amps. How much is going to continue up? Hopefully you can see what's coming in has to equal the 2 going out, so that one will be 4 amps. Depending upon what resistors determines how much current goes through each little path. Resistors here are the reciprocal function. Make sure that when you're calculating that R total, you remember to flip it at the very end. And notice the capacitors are opposite. Resistors and capacitors act oppositely. So when this one is the reciprocal function, this one will simply be added up. So why would we want to wire things in parallel? One of the main reasons that we want to wire things in parallel, so if the one branch breaks, the current will have an alternate path with which to travel. Hopefully your house is wired in parallel, and so if you want to turn off the closet light, the bathroom light can still be on. The disadvantage of wiring things in parallel is the extra wire, and as we were building this house and making the 5 million plugs and stuff that I wanted in this house, it took lots and lots and lots of wire to run the house in a parallel fashion that it is right now. This last little sentence is very important. Make sure you realize if we're calculating the total resistance, it will always be less than any single one resistor. And that becomes very important. If the total resistance is going to go down, and we have power is going to equal to V squared over R, if this, whoa, why am I going over here? Don't want that, sorry. If this resistance goes down, because we're wiring in parallel, that resistance is going to go down. Guess what my power is going to do? It's going to go way up. And you need to remember that power is the brightness of the bulbs. And so when things are wired in parallel, they will be much brighter than when they were wired in series. The light bulbs in this figure are identical and have identical resistance R. Which configuration produces more light? Wow, kind of just told you the answer there. It is going to be this one like here. Let's do the math, the dreaded math that y'all hate so much, in variable terms. So when I put these together, I'm going to get 2R there. In this case, 1 over R total is going to equal to 1 over R plus 1 over R. So 1 over R total is 2 over R, but I have to flip it, so it's going to be 1/2 R. And so hopefully you can see that this resistance of the total resistance is smaller than my smallest resistor. And so then to look at that power, power is going to equal to V squared over R, and I have to use that because my voltage is staying constant here. So I can plug this one in, and so it's going to equal to V squared over 2R for the first guy. This one's going to be equal to V squared over 1/2 R. That 2 is going to go up, and so that one will be greater. Which way do you think the headlights of the car are wired? They're wired in, they're going to be wired in parallel. So if one of the lights goes out, the other one will still be working. Here it is. The brightness of a light depends upon the power it produces. An object has more power, it will be brighter. Alright, last little bit here on this. Two 100 ohm resistors are connected in series and in parallel to a 24 volt battery. What is the current through each resistor and the equivalent resistance of the circuit? Hopefully you remember, you combine until you get, write this down, do it every single time. Combine until you have one resistor and one battery. Once you have one resistor and one battery, you will calculate the current, and then you'll work your way through up going back up around that. So let's work through a problem, and hopefully it's going to make more sense to you. I have a 100 ohm resistor and a 100 ohm resistor. My R total is going to be 100 plus 100. Guess what that is? Don't even have to get the calculator on that one. It's 200. So now I have a 200 ohm resistor. It's connected to a 24 volt battery. Now, if you have trouble keeping track of this path, change your colors. My volts is going to be 24 volts. My R is 100 ohms. I need to calculate my current. Hopefully you know the granddaddy of all equations will allow me to calculate that current. And I'll have 24 is going to equal that I times 200. I can perform this math, not in my head because I'm tired, but I can perform this math and get a current to be 0.12 amps. So, as I go back up, I know the current because one of these two numbers is going to stay the same. What is going to stay the same? V or I in series. If you don't know, look it up. I stays the same. So I write down my I because I know it has to stay 0.12 amps. Then when I do the math, I can see the voltage here will be 12 volts. The volts here will be 12 volts. Now, could you have said, 24 volts, two identical light bulbs, it's got to be split equally. Yes, you could. But this shows mathematically if it wasn't identical, how you could do that. So the total resistance here we calculated was 200 ohms, and we calculated the current going through each one. As we have these guys in parallel, the first step is to calculate our R total. So that's going to be 1 over 100 plus 1 over 100 is going to equal to 2 over 100. When I flip it, that gives me 50 ohms. So my R total is going to be 50 ohms. The battery, of course, is still worth 24 volts. And how much current then is being produced in this circuit? So as we do this math, we determine that current to be 0.48 amps. Again, how did I do that? Plugged into V equals IR. One of these two numbers is going to stay the same. What stays the same in parallel? In parallel, the voltage is going to stay the same. So I'm going to have 24 volts going through each one. And then I can calculate my current plugging again into V equals IR. And I will get 0.24 amps. And I is going to equal to 0.24 amps. If we want to see which light bulbs were brighter, hopefully you can compare. If I look at the power provided by that one compared to the power provided by the parallel path, you can see that that parallel path is great much more. The circuit has three identical light bulbs, each with resistance R. When the switch is closed, how will the brightness of bulbs A and B compare with C? What happens when the switch is open? Right now the switch is closed. Which light bulb is going to be brighter? If we follow along through the battery, does all of the current have to flow through C? The answer is yes. So when it is closed, bulb C will be very bright. Then what happens here at this junction point is that the current is going to be split. So A is going to equal to B, but it's going to be less bright than bulb C. Okay. When the switch is open, what is going to happen to our circuit diagram? Well, when it's open here, that's like bulb A is completely out. Hopefully you can see that this is a series path. So when it is open, C is going to equal to B. They're going to be equal because they are in series. Bulb A will be black because the switch is opening and it's not getting any current at all. Alright, that concludes part 2. We are going to stop it at that point and y'all work some problems.